Let's think about our system and heat and entropy moving in our system. So start off here on this slide talking about heat that flows into or out of the system, changing the entropy of the surroundings. And earlier we had this equation. We used a modified version of this actually in the last question there. So this will help us define the entropy change of the surroundings based on the heat change for the system. And we made a little modification to that. This is the modification that we used actually in the last problem there. We said we are going to define that the pressure is not changing. So there's no change in pressure. We're just doing this experiment, whatever it is we're doing, out on the countertop. So that means that Q is going to be the same as enthalpy for our system. So the heat change is going to be the same as the enthalpy change. We also said earlier that the universe, the entropy change, I should say, of the universe, is just the same as the entropy change of the system and the entropy change of the surroundings added together. And we also said that for spontaneous processes, this entropy change of the universe is always greater than 0. So if we take all these things that we've discussed already and put them together, take that first equation, we go ahead and substitute in the enthalpy for Q, and then we take this, delta S for the surroundings, and we plug it in to this equation here, because it's the same thing. It's the entropy change for the surroundings. So we plug that in for, we plug in delta H, or negative delta H for the system, over T for delta S of the surroundings. And we're left with this equation, which if we do a little bit of algebra and rearranging, so what we're going to do here is we're going to multiply everything by T, and then do some subtraction and stuff to get this by itself on one side. We get this equation. This equation, excuse me, has both the enthalpy change of the system and the entropy change of the system in one equation. Both of the things that determine if a reaction is spontaneous, the enthalpy and the entropy. A guy named Gibbs, and I cannot remember his first name for some reason, but Gibbs, that's him right here, not this Gibbs, he took that other part of the equation. So we had this stuff over here, the enthalpy change of the system minus T times the entropy change of the system. That is equal to negative the temperature in Kelvin times the entropy change of the universe. He took that and he defined it as a new value, and he called it the Gibbs free energy, or actually I think he just called it the free energy, and it was named after him later. It's now called the Gibbs free energy. We know that when delta S of the universe is positive, reactions are spontaneous. And so if delta S of the universe is positive, then inside of this, what that means is that that whole thing is going to end up being negative, because if this section of it is positive, then having the negative there is going to mean that the whole thing is going to end up being negative. So when Gibbs free energy is negative, that will tell us that a process is spontaneous. So what this means is, if we have some way of finding the enthalpy change of a process and the entropy change of a process, and we know the temperature at which the process is occurring, we can figure out, will this process happen spontaneously or not, based on whether this delta G value here ends up being positive or negative. So negative delta G means that our process is spontaneous, and a positive delta G means that it is non-spontaneous. Now, if delta G is positive, does that mean that the process is impossible? No, it's not impossible. It just means it's not going to happen all by itself. Something needs to come along and give it a push, essentially. Something has to help it happen. But it's not impossible. Um, right now, I'm sitting in my room and I can see a sock on the floor. Could the sock rise up into the air? No, not on its own, but I could go over there and pick it up. So processes that are not spontaneous are not impossible. It just means that something has to kind of give it a little help. Something has to help it happen. And later, I will be helping that sock get into the hamper. A non-spontaneous process that will happen because I will burn energy to walk across the room and pick it up and put it in that hamper. So non-spontaneous processes, they happen all the time. They just don't happen all on their own. Something has to give them a push. And this actually relates back to our discussion of equilibria very, very well. So Gibbs free energy, for example, if we have a system that is at equilibrium, the Gibbs free energy value for that system is always 0. So let me say that a slightly different way. If we have a Gibbs free energy of 0 for any reaction that we're looking at, what that means is that that reaction is at equilibrium. It doesn't mean that the reaction has stopped, because again, equilibria, you don't have the reaction stopping at that point. We just have no overall movement. It's not going forward, it's not going backwards. There's no overall movement in the concentrations of materials. So Gibbs free energy of 0 means that we have something at equilibrium. If we have a Gibbs free energy that is negative, that means the process is spontaneous. That does not mean that it's going to always be spontaneous, though. That doesn't mean that that particular process is going to keep going and keep going and keep going, because the process that we're considering at this point is a chemical reaction. And so it will keep going to a point until it reaches equilibrium. And so that's what we can see here. If we have a free energy that is negative, excuse me, the reaction is going to continue until it reaches the equilibrium, at which point it stops. In the same way here, if we have, if somehow we made a mixture of materials and we had essentially gone past the equilibrium, it would still be spontaneous. It would just be spontaneous now in the opposite direction. So if we have a Gibbs free energy that is positive, that doesn't mean that nothing is happening. That means that the opposite of what we have written is happening. The reverse reaction is spontaneous. So just trying to help you get a better idea of what the Gibbs free energy is actually telling us. So a negative Gibbs free energy value is saying that the reaction as we have written it and at the temperature at which it's happening will occur spontaneously. If it's 0, that means that we're at equilibrium, and so there's no overall movement in the reaction. And if we have a delta G that is positive, that means that the reaction that we have written is not spontaneous. The opposite reaction is spontaneous. The reverse process is spontaneous. If we take a look at that equation again, go ahead and write it here. So delta G is equal to delta H minus T delta S. So if we know just the signs of these two things, because the temperature can never be negative. Temperature is always going to be in Kelvin, so it's always positive. But delta H and delta S can be either positive or negative. Just knowing the signs of these two things can actually tell us whether the process is spontaneous or not. Even without having the numerical values, sometimes we will have enough information to tell if the reaction is spontaneous or not. And in the situations where we don't have enough information to tell if the reaction is spontaneous, we still have some information. We can still make some statements about the reaction. So for example, we'll start with this box here. So if we have delta H that is negative and delta S that is positive, so we have an exothermic reaction. It's releasing heat to the surroundings, and we get an increase in entropy. These reactions are spontaneous at any temperature because both delta H and delta S like the reaction, essentially. They are both trying to make the reaction spontaneous. It kind of gets back to, if you remember from the second chapter, thinking about the big brother and the little brother. The big brother was the enthalpy value, and the little brother was the entropy. In this case, they're both in agreement. They both want the reaction to move forward. If, on the other hand, delta H is positive, so that would be endothermic, and delta S is positive, so they're both positive in this case, now the enthalpy does not want the reaction to move forward. So it is unfavorable in terms of its enthalpy, but entropy is still there saying, I want this reaction to occur. So in situations like this, where this one, the delta H, is saying no spontaneous reaction, and delta S is saying yes, I want a spontaneous reaction, usually what happens is the reaction is not spontaneous at low temperatures, but is spontaneous at high temperatures. And the reason for that is usually delta H is bigger, most of the time, than delta S. But if that temperature part of the equation gets bigger and bigger and bigger and bigger, that will eventually overwhelm delta H. It's different for each reaction at what point that happens, but eventually, if you keep increasing the temperature, this part of the equation will become larger than delta H, and you will have a spontaneous reaction. So the opposite is true if enthalpy is favoring a reaction and entropy is disfavoring. So if you have a negative delta H, which again is an exothermic reaction, and entropy is saying, don't want it, don't want this reaction to happen. At low temperatures, this tends to be spontaneous, and at high temperatures, it tends to be non-spontaneous. Because again, if you get it hot enough, this section, which is multiplied by the temperature, will overwhelm the enthalpy value. And so then the last possibility here is if they both agree, no. If they both say, we don't want this reaction occurring, then it's not spontaneous at any temperature. So if you have an endothermic reaction and the entropy is not increasing, the entropy is decreasing, then nobody wants this thing to happen. And so it is not going to be spontaneous no matter how hot or how cold you get it. So simply by knowing the sign of delta H and delta S, we can get good information about whether the reaction is likely to be spontaneous or must be spontaneous, depending on those signs. All right, I know this is kind of a long one, but we'll get this one practice problem worked, and then we'll call it the end of this video. So we have a question that's asking us to consider the reaction for the decomposition of carbon tetrachloride gas. They give us both delta H, which is 95.7 kilojoules, and that's positive. And they also give us delta S, which is positive 142.2 joules per Kelvin. So notice here, both of them are positive. That is going to put us here in this realm, because we have an endothermic reaction and the entropy is increasing. And so we don't know actually, just from looking at those signs, whether the reaction is going to be spontaneous or not. So we're asked to find delta G at 25 degrees C and determine whether the reaction is spontaneous. Well, we know delta G is equal to delta H minus T delta S. So if we just plug in what we know, delta H is 95.7 times 10 to the third joules. And I'm doing that conversion there because I need the joules and the kilojoules to be in the same unit. So I'm just going to go ahead and put that one into joules. And then I have minus 298 Kelvin times 142.2 joules per Kelvin. All right, so those kelvins are going to cancel out. And if I do the math here, let's see, 95.7 times 10 to the third minus 298 times 142.2. is? Delta G is 53,300, and I'll just cut it off there, joules. Or 53 point, oops, 53, not 55.3 kilojoules. And that is positive. So what that tells us is that this reaction at this temperature is not spontaneous. Because again, remember, delta G values that are positive, not spontaneous. Negative delta G values are spontaneous. So then part B says, if the reaction is not spontaneous, oh, who'd have thunk, it's not spontaneous. Determine at what temperature, if any, the reaction becomes spontaneous. So, if you will, pause the video for just a second and try to think of a way that we could determine how hot would we have to get this to make it spontaneous. So think about that for just a minute. Okay, hopefully you paused the video and thought about that. If you remember a discussion from a couple slides ago, we said that if you get to a delta G of 0, that means you're at equilibrium. If we get this hot enough, because if you notice here, delta S wants the reaction to be spontaneous. It's the enthalpy that wants it to be non-spontaneous. So at 25 degrees C, the enthalpy is winning. If we heat this up, though, the delta S section of the equation will get bigger and bigger. So eventually, we'll reach a point where delta G is 0. And anything higher than that, it will become spontaneous. So what we're going to do is we're just going to say delta G is 0. So we're going to set everything equal to 0. So 0 is equal to 95.7 times 10 to the third joules minus T, we don't know what temperature it is yet, times 142.2 joules per K. And so if we work out the algebra here, let's see, we're going to have the 95.7 times 10 to the third. And we're going to subtract that from both sides. So we'll end up with negative 95.7 times 10 to the third joules on the left side. And so then we'll divide both sides by negative 142.2. So those two negatives will end up canceling each other out. And the temperature that gives us is 673 Kelvin. Really, really hot. So is it possible for this reaction to be spontaneous? Yes. You just have to get it above 673 Kelvin. Because remember, at 673, it's at equilibrium. That's when delta G is 0. That's at equilibrium. So we have to get it higher than that temperature. But if we can do that, then it will be spontaneous. All right. Hope that made sense. I will see you in the next video, and we'll have a brief introduction to the third law and final law of thermodynamics.